Hello, everyone. Thanks for coming to the talk. I'm Naman Agarwal, and I'll be presenting our work, A Deep Conditioning Treatment of Neural Networks. This is joint work with Pranjal Awasthi and Satyen Kale. So let's dive into the motivation for this work. Deep learning, as we all know, has enjoyed tremendous practical success in the last decade or so, and we know that the depth plays a really crucial role in this. Depth, however, comes with its own difficulties in terms of tractability and stability in training, and multiple interventions are required to train really deep networks. One such ubiquitous intervention is given by normalization layers, which come in multiple forms, things like batch norm, layer norm, and various others. While these interventions are extremely popular to the extent of being necessary in training deep networks, we understand very little theoretically about the actual role played by these normalizations, whether it be in terms of training dynamics or shaping of the optimization landscape, amongst other aspects. In this work, we investigate improved data conditioning as a possible factor towards explaining some of the effects of depth and normalization. Our hypothesis in particular is that nonlinear activations under appropriate normalization in neural networks lead to conditioning of the last layer representations, and this conditioning continuously improves as we take deeper and deeper networks. Simple optimization theory tells us that better conditioning naturally helps optimization by making the landscape more isotropic. When we tested this empirically, we see that when under common forms of normalization, such as batch norm and layer norm, data, as training progresses, both test and train, gets better conditioned as accuracy increases. Conditioning here is given by normalized dot products, which reduce over time. The intuition for the conditioning hypothesis stems from an earlier work of Das et al., which shows in a restricted setting with specific activations that if we take randomly initialized wide neural networks and pass through it two inputs, we see that their representations continue to get further separated as they pass through the network, eventually approaching orthogonality. If we plot the behavior of in a simple setting with sign activation, we also see that very quickly the normalized dot products reach zero as depth increases. This in particular implies that if we look at the kernel matrix generated by the last layer representation, it approaches towards identity very quickly as we increase the depth. This is the notion of conditioning the results in this paper are targeted towards. With this context, let me lay out the main contributions of our work. We show that for very large, fully connected networks, for any nonlinear activation, the conditioning of the representation improves exponentially as depth increases. In doing so, we also characterize the multiplicative factor for this increase, showing that it depends on a measure of nonlinearity of the activations. In other words, the more nonlinear, in a certain sense, the activations are, the faster this improvement of data conditioning is. As part of the result, we also clarify the role certain normalizations of the activation function play in terms of the conditioning. These normalizations correspond to the mean of the activation or the variance of the activation under the Gaussian measure. As for the conditioning results, we provide them for the representations at the last layer obtained at random initialization. This, of course, corresponds to optimization benefits when only the last layer is trained. And we further provide results for the neural tangent kernel as well, which corresponds to training the entire network to convergence with an extremely slow learning rate, which has also been called the lazy training regime. Having established the role of normalizations in our analysis, we propose a new activation function NormReLU, which is a shifted and scaled version of the standard ReLU. This satisfies our theory. Through simple preliminary experiments on deep image classification, we show that NormReLU shows potential towards replacing normalization techniques like batch norm and layer norm in practical deep learning. Before describing our core results, let me set up some basic notation and background. We assume that the dataset is composed of unit vectors for simplicity and that none of them are collinear. That is, all of them are at least delta separated. While the separation assumption is necessary to obtain conditioning, the main paper provides results even when input vectors are not unit norm. To set up further notation, we assume that the neural network is fully connected with a constant width m and a total depth d. We will assume that the weights of the neural networks, as is common practice, are initialized as independent unit Gaussians, and we assume the so-called NTK parameterization wherein the post activations are divided by the square root of the width. Under this setup, given an input, we denote the representation obtained by at the last layer by phi of x, and the main object of our interest is the kernel matrix obtained by the gram matrix of these representations. It is well known that if the width approaches infinity, this kernel approaches a deterministic limit, which we denote also by the letter k. Before moving further, we state some normalization assumptions we make on the activation function sigma for our results. The assumptions state that the activation should be normalized with respect to the Gaussian measure in the following two senses. It should be centered with mean 0, and it should be such that its variance is equal to 1. While the second assumption is perhaps benign as it can be ensured by simple scaling, the first assumption, while non-standard, turns out to be necessary towards achieving perfect conditioning. Many common activations satisfy the assumption simply by the virtue of being odd functions. However, the standard ReLU function does not satisfy the assumption. And indeed, for the ReLU function, as we show, the conditioning does not happen. Consequently, later we propose a modification of the standard ReLU via a family of ReLU-like functions that satisfy the assumption. While not relevant to this talk, in the full paper, we also provide an analysis for the case when the centering assumption is not satisfied, and we show that angles converge to a non-zero finite value instead of converging to a zero value as with perfect conditioning. We are now ready to state our first main result, which deals with the kernel matrix obtained by the last layer representations. To state the result, we require the notion of the non-linearity coefficient, which is given by the following expression. The important part to note here is that mu, this coefficient of nonlinearity, is 0 if and only if the activation is a linear function. And in this sense, how far mu is away from 0 captures how nonlinear the activation is. Our main result in the paper shows that as width approaches infinity and the depth is larger than a function of the initial separation and mu, then the inner products of the representation decay exponentially. The exponent of the decay depends on the depth, and the rate of decay is determined by how far the function is from linearity given by the coefficient mu. This result can be easily extended to show a condition number bound on the kernel matrix approaching 1 at a similar exponential rate as the main theorem. We further show essentially the same result for the neural tangent kernel, with exponential decay of the kernel entries. As a reminder, the NTK corresponds to the optimization dynamics corresponding to training all layers with a small learning rate. A similar bound on the condition number of the NTK can also be obtained from this result, similar to what we saw in the last slide. Let me now provide a very quick proof overview of our main result. Suppose we have an input pair x, y with rho denoting their inner product, and suppose we pass it through one layer of the network. We are interested in the inner product of the representations obtained at the end of this layer. An easy calculation shows that the inner product is equal to the expectation of the product of the first coordinate of the post activation. This is denoted by phi1 in the slide, and this is a byproduct of the fact that we have assumed infinite width networks. Laying out the expression for phi sub 1, we see that this depends on the quantities x transpose w and y transpose w, where w are the weights of the layer. Since w is sampled from a unit Gaussian, it is easy to observe that these random variables, x transpose w and y transpose w, are distributed as row correlated standard Gaussians. Therefore, the expression for the inner product simplifies as the following expression, depending only on the original inner product row. Okay, this function, which was considered by Danieli et al., we call it as the dual activation function and denoted by sigma hat of rho. This is the function because this is the function that transfers the inner product of the input to the inner product of the representation, and this is the function that we need to bound. To bound this function, we make use of the Hermite polynomial basis expansion of the activation function, which leads to a very clean expression for the dual function based only on the Hermite coefficients of the original activation. Now, our assumptions on the normalization of the activations lead to very particular conditions on these Hermite coefficients. And using these, with a little bit more calculation, one can show that sigma of rho, sigma hat of rho is in fact smaller than rho always, and the shrinkage depends on mu. Okay, so we get the result that we wanted across a layer in a product's decrease, and when we repeat this across layers, we get the exponential decay that we mentioned. Finally, motivated by the normalization assumptions, we propose a shifted and scaled version of the ReLU function, which we call normReLU. Via some preliminary experiments on ResNets as well as on fully connected networks, we see that the train and test performance of the norm ReLU remains similar when we replace the batch norm operation by the norm ReLU activation. We end this talk with a short description of some applications / implications of our results. For optimization, we show that for a deep enough network, gradient with square loss converges at a logarithmic rate independent of the initial conditioning. Further, we show that for learning random neural networks, exponential in-depth queries are required in the statistical query model. And lastly, we show that we show an excess risk bound for the minimum norm interpolating classifier for linear regression with an RKHS given by the kernel K, which is generated by a random deep neural network. We request the audience to see the full paper for a detailed description of these applications. With this, we end the talk. See you in the questions session. Thank you.